Okay, hello. We are going to go ahead and start section 2.2 today, which has to do with the topic of linear functions, hopefully a topic that you have been introduced before to in Algebra 1. I want to just start out first of all with looking at how the equations for linear graphs look. Okay, first of all, when we talk about a linear equation, we are talking about graphs that are completely straight. Okay, this means that they have no curves to them at all. Okay, and I'm just going to specify a little bit further that a linear equation or a linear graph is also not vertical, so no vertical lines. Okay, no vertical lines would be included in that. Okay, so when we talk about linear graphs, we are talking about lines that are completely straight and they are tilted in one manner or another. Actually, even horizontal lines qualify as being a linear graph, just not vertical. Okay, and so what I want you to be able to do is I want you to be able to answer questions like this, where you're asked to look at equations, not the graph, and be able to decipher yes or no whether that equation is representing a linear function. And that means if you were to graph it, the graphs would be these straight but not vertical lines. So we're going to go back up to the top here again, and you're going to see that I have three different things listed here. Okay, the first one says that the equations have to have a variable raised to the first power, no higher. Okay, so if you're seeing something like an x squared or an x cubed, that automatically is going to disqualify that equation from being linear. I'll just draw your attention to the fact that on example F, and this is already filled out on your notes page for you, you can see here that for us to say whether this is a linear function, again, yes or no, we're responding no, this would not be linear, because we can see that the exponent is definitely higher than 1. We can see it's 3 there. Okay. The intent for these 6 problems here are not for you to try to graph these on your calculator and look at the graph, but rather be able to look at the equation and pinpoint if there's some type of violation happening in the equation that would lead you to say that it's not a linear equation. Okay, so back up to the top, let's look at number 2 here. It says the variable has to be in the numerator. It cannot be in the denominator. Okay, and here's one thing that we know about variables that are in the denominator. I don't see any of the examples like this. I don't know that you're going to run into any like this, but when you have a negative exponent, okay, any negative exponent technically means that that variable would then be moved to the opposite location. In this example I just drafted here, that means it would be moved to the denominator. But you can see, and I went ahead and filled out A, B, and C for you. I want you to go ahead and copy these down. You can see in example B how the variable is in the denominator, so that disqualifies this graph from being a linear graph, and this is no longer a linear equation. We're going to say no, and our reason, instead to explain, is that there's a variable in the denominator. Okay. The last thing up top here, number 3, it says the variable is not allowed to be multiplied by other variables. And so you can see also in example 3, which I'll have you copy down, that here we have 2 variables, x and y, multiplied together. That is disqualifying this from being a linear function. My reason, 2 variables are being multiplied. Okay, A looks pretty good. In fact, we know that to be a linear equation, it typically takes on the model, what we refer to as slope-intercept form, honestly, something that you've been familiar with, mx plus b. That is how you can write all linear functions, okay? All right, so the first few problems on your homework assignment are going to be very, very similar to how these 6 problems right here are. Okay, we're going to move on down to a word problem here. It says the growth rate of a sample of Bermuda grass is given by the function f of x equals 5.9x plus 3.25, where f of x is the total height in inches and x is the days after the initial measurement. Okay, so what's very important with word problems is that you guys are identifying what your y variable is representing and what your x variable is representing. And of course we know that f of x is the symbol that is representing the y variable. Okay, so y is height of the Bermuda grass, x is how many days have passed since it was initially measured. Okay, if you can distinguish what your two variables represent, then when you get down to part A, you can just ask yourself, okay, what's this question asking? How tall is the sample after 3 days? Well, this number 3 is labeled in days, so that means that 3 needs to be plugged in for an x, because it's set up here that x is the number of days, okay? So the way we do this in math is when you write f of 3, that's the notation that means that on the other side of the equation, you're going to be substituting a 3 in for the x. That will then give you an answer of 20.95, and that should be labeled in inches, because that is your answer, is the height of the grass after 3 days. Okay. Now, part B, though, says the term 3.25, okay, that's referring to this right here, 3.25 in the equation, represents the height of the grass. Okay, it's the height of the grass when it was initially measured. The sample after 3 days is how many times as tall as the initial height. Okay, just to make sure this makes sense to you, the initial measurement would happen on day 0. Okay, so if we were to plug a 0 into the equation for x, you can see that your answer is the 3.25, that the problem is saying that was the initial height. Okay, so we want to know how many times, or excuse me, the sample after 3 days is how many times as tall as the initial height. Okay, so we're going to take what the height is after 3 days, and we want to figure out, well, how many times does the 3.25, the initial height, fit into that? And it goes in, and I've rounded here, it's approximately 6.45 times as tall. Okay, so that initial height was multiplied by 6.45. Okay, and then finally in part C, it says if the Bermuda grass is 50.45 inches, okay, now I'm looking at this number and I'm seeing, okay, this number is not days, this number is talking about height, which is the y variable. The question is, how many days has it been since it was last cut? And so here, we're going to go back to the equation in the original problem here, plug 50.45 all the way on the left side for the y variable, the height, and then we're just going to use our algebra skills to solve this equation for x, the number of days. Okay, and we know that we would subtract 3.25 from both sides. That would leave us with 47.2 on the left, and then finally we would divide both sides by 5.9, leaving us roughly with an answer of, it would be 8 days for it to have grown to the 50.45 inches there. Okay? All right, hopefully you didn't have too much trouble with that. Now, the next thing we're going to talk about is we're going to talk about what's known as standard form. Standard form is something that's not used a lot in algebra. It is a different way that you can express an equation. I think you are most familiar with having equations in the slope-intercept form. Standard form is a few things. One, it is when you are placing the x and the y variable together on the same side of the equation, as opposed to in slope-intercept form, you're getting the y by itself. Okay. A few more things though. You always have to have your x term first, and your y term has to come second, and what you're putting on the other side of the equation is the constant that's in your equation. Okay. A couple other things worth noting here. A, B, and C are not allowed to be fractions, so if they are, we'll need to get rid of those, and I'll show you how to do that. Also, A, which would be the number in front of the x, that must be greater than or equal to 0. So in other words, what that means is the A must be positive. Okay, has to be positive. And A and B cannot both be 0, okay? So let's take a look at example 3A. This is definitely the more difficult of these 3 problems here, okay? I'm just going to rewrite this so that my fraction looks a little bit better, okay? We certainly can agree that the x and the y are not on the same side of the equation right now, so we want to shift and pull that 8y to the left side. We would do that by subtracting, okay? But as I look at this, I see, we're saying that A, B, and C all are supposed to be integers, not fractions, and I see that my A value is actually a fraction here. Okay, this is very easy to get rid of fractions. All you're going to do is you're going to take whatever the denominator is in that fraction, and you are going to multiply both sides of the equation by that denominator. Now I'm going to do something else here too. In addition to multiplying both sides of the equation by 10, since another requirement is that that a value has to be positive, and I see right now that it's -3/10, I'm going to distribute a -10 to both sides of the equation, okay? And when I do that, what will happen is my 10s will cancel in the fraction, leaving me with 30x. Okay, my number in front of the y will now be a positive 80, and then the number all the way on the right side of the equation will be 140. And so I've got it in standard form now. Wants me to identify A, B, and C, and that is simply 30, 80, and 150. Okay, let's take a quick look here at the next example. My first step is to pull the x and the y so they are on the same side of the equation. So I'm going to drag that -4x over. Okay, my next step is to make sure that I don't have any fractions, which I don't. But then my final step is I need to make sure that the a value is positive. It is not. So I'm simply going to multiply everything on the left side and everything on the right side by a -1, and that will make that positive there. Okay, so here we are in standard form. Okay, and there's the A, B, and the C. Okay, so let's take a look at the back here, a couple examples here on the back that have to do with x and y intercepts. Okay, when we talk about x and y intercepts here, I think that you are familiar with what these are referring to. A y-intercept is where the line crosses the x-axis, and an x-intercept is where the line crosses the x-axis. Okay, here's one thing that you just want to think about is if we're talking about a y-intercept, what all of these points that are on the y-axis, what all those coordinates have in common with each other is they all have x values of 0, okay? And so what we want to do here in example 4, it's asking us to find both the x-intercept and the y-intercept for this graph here, okay, and then they want us to graph the equation. Now this is where standard form is actually very, very helpful. Okay, you can see that we have both the x and the y on the same side. I will say this isn't quite in standard form, and we need to make one small adjustment, so I'm going to write that here. That constant of 8 needs to be moved to the other side. We, of course, would subtract that 8, and that would make that a -8 on that side. Okay, now I'm going to do the y-intercept first, because we said right here that what all y-intercepts have in common is they all have a 0 for the x. Okay, so if I were to take my equation and substitute a 0 in for the x, it kind of wipes that term out, and if I keep solving for y, I discover that the y-intercept for this graph is at 0, 8/3, or I could write that 0, 2 2/3. Okay, so I'm going to go ahead and plot that up to, I'm just going to estimate roughly right there's about 2 2/3, we'll say. Okay, now I can make the exact same argument for x-intercepts. All the points that you would put on the x-axis, guess what? What they all have in common is they all have a 0 as the y-coordinate. Okay, so I'm going to take my equation in standard form, only this time I'm going to substitute a 0 in for the y. Okay, and then I will solve for x. That gives me -4. That means the x-intercept is at -4, 0. And when you're graphing linear equations, you only need 2 points to draw a straight line. I have those 2 points. I would simply connect them to make my line. Okay, notice that I did not put this in slope-intercept form and then graph it from there. Okay. The other thing I'll just draw your attention to up here is there are some terms that can be used interchangeably. If you hear the phrase roots or zeros, those are all just synonyms for x-intercepts. Okay. All right, we're going to take a quick look here at this next example. Same thing here, not quite in standard form, but almost. Okay, we're going to move the 10 to the other side. When I'm doing an x-intercept, that is when I will plug a 0 in for the y. So I'm going to plug a 0 right there for the y. I will go ahead and solve this for x, and then I'm going to come over to my graph and I'm going to put a point where x is 5. Okay, when I'm finding the y-intercept, I will then plug 0 in for the x. Okay, and then I will go ahead and solve what's left for y, and then I will plot that point on the y-axis, and again, I'm going to connect those 2 points together to form the graph there. Okay, now you'll notice on this last one here, it's a little bit different because the equation isn't quite in standard form. Okay, it's more in slope-intercept form, and that's fine to graph it, but that's not really super helpful, at least for the x-intercept. You could make the argument that you can kind of see what the y-intercept is kind of from that equation, and that would be okay. But I'm going to go ahead and put this in standard form. I'm going to bring the x to the left side, so it's on the same side as the y. And then technically standard form is making sure that that a value is positive. So I'm going to make that 3x minus y equals 9. And then for the x-intercept, here's where I'm going to plug 0 in for the y. Okay. As I do that and then solve for x, I get that my x-intercept is at 3, 0. My y-intercept, 1, 2, 3, 4, 5, 6, 7, I think we're down here, and then we would simply connect those two. Okay, your homework assignment is to complete worksheet 2.2a. All right, thanks so much.